Chapter 19, Lesson 3. In this chapter, we have been trying to answer this question: why do some reactions spontaneously occur and others do not occur? In other words, why do chemical reactions happen? And we had talked about two factors that contribute to any chemical equation or any chemical reaction, and those two factors were delta H, which is enthalpy or heat change, and delta S, which is entropy or disorder. Now, we said that systems want to decrease their thermal energy, so delta H is favored to be negative. In other words, nature wants to always release energy, wants to go to a lower energy state. And likewise, nature wants to increase disorder, so delta S is favored in the positive direction. Now, we're going to put these two ideas together into one equation and define something called delta G, which is called Gibbs free energy, named after Josiah Gibbs, a scientist that first developed the idea. Now, here we combine delta H, enthalpy, delta S, entropy, and there's also a temperature factor. Now, we had said pretty early on in the first lesson that temperature affects the decision whether nature will force a reaction forward or not. For example, water will become ice at a sufficiently low temperature and will not become ice at a sufficiently high temperature. So temperature is a factor. And the equation looks like this: delta G equals delta H minus T delta S. This is probably the most famous equation for thermodynamics. A very important equation. Good idea to memorize it, but a good idea really to understand what it's saying. And that's what we're going to try to define in this lesson. So before we go into the details of the equation, anytime delta G is negative, the reaction is spontaneous. So delta G essentially measures whether the reaction will happen or not. And remember, spontaneous means that nature will force it to happen on its own. And so delta G being negative, you can think of this as the release of overall energy, and that way it'll go on its own. If delta G is 0, then the reaction is at equilibrium and will not go either way. We have actually reached equilibrium. And if delta G is positive, the reaction will not go on its own, so it is non-spontaneous. We can make the reaction go by applying work. More work must be supplied to make it occur. And the reverse reaction then will be spontaneous. So by looking at delta G, we can predict whether it's going to be spontaneous or not, or whether nature will make it happen or not, depending if it's negative or positive. So if you take a look, this is kind of a diagram of this equation here, and this kind of shows the equilibrium idea. If you have reactants becoming products, if you have pure reactants, then nature will spontaneously go toward the products. If you begin with pure products, nature will spontaneously go toward reactants, and they will meet in the middle, and they'll meet at K, at the equilibrium mixture. So equilibrium will definitely play a role, and this is kind of a visual way of what was described on the previous slide. So equilibrium means delta G is 0. Spontaneous in the forward direction means delta G is negative, and non-spontaneous in the forward direction means delta G is positive, if we were to go this way, for example. Now, we can also do the same thing we've done with delta H's and delta S's with delta G's. In other words, if you want to know the delta G for a process, a specific process, you could do the delta G of products minus the delta G of reactants. And these, just like delta H and delta S, are found in Appendix C. So delta G's are listed along with delta H's and delta S's, and they've been tabulated for your convenience. You could technically find delta G's if you have delta H and delta S. That's really all you need, but they've been tabulated for many reactions, so we can go directly and find the spontaneity of a chemical equation. We can predict whether a reaction will happen or not by looking directly at the delta G's. In fact, let's go ahead and do that. So in A, we're going to do like a theoretical prediction, and in B, we'll do an actual calculation. So we're asked to predict whether delta G for the reaction is more negative or less negative than delta H. We can't, just by looking at the equation, we can't really predict whether nature will make it happen or not. We have to have delta H values and we have to have delta S values. But we can actually get some idea of what will happen in terms of delta H. So here it says, let's find out what happens to the delta G. Now our overall equation says this: delta G equals delta H minus T delta S. And so we know that delta H is negative. In this equation, notice delta H, heat enthalpy, is negative. So we'll make this a negative number. Now if you take a look at the equation itself, we have 5 plus 1, we have 6 moles of gas on the left side. And we have 3 moles of gas on the right side. We also have 4 moles of liquid. Remember we said that entropy, we want to find the general entropy change, general delta S for this reaction. We said that liquids are more ordered than gases, and because we have more gas on the left side, we decrease the amount of gas, so we decrease disorder. So delta S will actually be negative. So just qualitatively, we can calculate the delta S from the back of the book, but just looking at the equation, we can predict that the delta S is negative. And in fact, if delta S is negative, here's what we've got. What we have is we have a negative delta H minus a negative delta S. So overall, this term overall will end up becoming positive. We're subtracting a negative, which is the same as adding. So what will happen is delta G will actually be smaller or less negative, because if we have a big negative number, here it is, plus some other number. We don't really know, we can calculate, but we can theoretically predict that delta G will be less negative. So here's the answer, less negative. And we were able to obtain this by just the analysis of this equation. We can do the actual calculation. There are 2 ways to use Appendix C to do this calculation. We can do products minus reactants because we have access to delta G values, or we can do delta H values, obtain those from the Appendix C, obtain delta S values, and then add them together. The shorter way is actually just to get products minus reactants. So why don't we do that? Let's do delta G equals products minus reactants. In this case, let's see if we could find delta G values, and I'll write the delta G values. Let's see if we can get rid of some of these here, and we'll write the delta G values for the reaction above. So looking at C3H8, finding the delta G value in Appendix C, negative 23.47. And these will all be in kilojoules. Then finding O2, delta G, if you look in the back of the book, will say 0. Now this is because just like delta H's, delta G's will be 0 for elements, because delta G is a measure of whether the reaction to form the element will go forward, and since it's already an element, we have a 0 value. For CO2, this value should be under carbon, negative 394.4 kilojoules. And finally, water should be under oxygen. Make sure you take liquid water. Keep track of the state symbols. Negative 237.13 kilojoules. So let's go ahead and add up the products and subtract the reactants. So in our case, we have products for waters. So 4 times negative 237.13 plus 3 times negative 394.4. These are our products minus our reactants, and since oxygen is 0, we won't include it, but we will include the negative 223.47. So let's go ahead and plug these numbers into your calculator. I suggest doing this step by step and not trying to put everything in the calculator at the same time, as you're apt to make mistakes that way. 4 times negative 237.13 gets us negative 948.52. 3 times 394.4, negative 394.4, gets us negative 1183.2. Combining these two values, we get 948.52, a big negative, which is understandable, negative 2,131.72, and then we're subtracting a negative, so here these combine together to form a positive. So essentially we're adding 23.47. So plus 23.47, and we get our final answer to be negative 2,108 kilojoules. And that would be the final answer. Now notice we predicted it to be less negative, and in fact, if you take a look, it is less negative. And not by much, but it is less negative. It's more to the positive side, so about 110 or so kilojoules closer to the positive direction. So we can do these calculations and determine delta G's. So this reaction, by the way, looking at this reaction, knowing that delta G is very negative, then nature will make this reaction go on its own. In fact, this is a simple combustion reaction. This is the burning of propane, and we know that the burning of propane does happen. If you let it set it off, nature will make it go on its own. Okay, so let's go ahead and see if we can take a look at the central equation and make sense of it. This is the central equation of the chapter. There are 4 possibilities for delta H and delta S, and those possibilities will determine whether the reaction is overall spontaneous. So if delta H is negative and delta S is positive, here's what we've got. We've got delta H being negative, delta S being positive, so we end up doing minus a negative number minus another number, and we're becoming more negative. In other words, our negative is becoming bigger because we're subtracting from an already negative number, which means delta G will always be negative. And if delta G is negative, remember, that means the process is spontaneous. And no matter what the values are, as long as these are the signs, delta G will always be negative. It's impossible for delta G not to be negative. This essentially is, here's what this means. Remember, we said that delta H, nature wants delta H to be negative. This means it releases heat. Nature wants delta S to be positive. It means it increases in disorder. So if both of these factors are going for nature, nature will definitely say, yes, I will run the reaction. It's going to be spontaneous because I have 2 of these factors going for me. Okay, let's take a look at the other scenario. Take a look at now if delta H is positive and delta S is negative. So we have delta H being positive, delta S being negative. We have ourselves a positive minus a negative. So this overall term is a plus because we're subtracting a negative or adding a positive. And for the overall, we get a positive delta G. Now remember that positive delta G means it is non-spontaneous. Nature will not make it run. And this makes sense because delta H, nature wants delta H to be negative. It does not like to add heat to the system, and it does not like to decrease disorder. So both of these factors are going against nature, and nature will never make this happen. So it's non-spontaneous at all temperatures. The third possibility is if both of them are negative. If delta H is negative, this is going for nature. Delta S is negative, this is going against nature. We have a delta H that's negative, a delta S that's negative. We have a negative number minus another negative. Again, this term becomes positive. And here is where it depends how big this term is. if this term is sufficiently large, it will outweigh the negative and make the overall delta G positive. If, however, delta S is not sufficiently large, then it'll remain a negative. So here, it all depends on the temperature. In other words, if the temperature is high enough, then this factor will outweigh delta H. And what this means is that if delta S, if you heat it up enough, delta S will have increased by enough to where we could run the reaction the other way. It's kind of the idea. So when one of them is going for nature and the other one is not, it all depends on temperature. So it'll be spontaneous at low temperature. That's because when the temperature is a small number, then we will not be able to outweigh delta H. But when the temperature is a high value, we will be able to outweigh delta H. So it'll be non-spontaneous. And the final scenario is very similar. If both of them are positive, we've got one working for nature, delta S is working for nature, delta H is working against nature. So this is positive, and this is positive. So we have a positive minus a positive, so effectively this term is negative. At sufficiently large temperatures, this term will be able to outweigh delta H and give us an overall negative number. At low temperatures, it will not be able to outweigh and give us a positive number. So it's spontaneous at high temperatures and non-spontaneous at low temperatures. So this equation essentially describes to us all the possibilities of how nature will run or not run a reaction. This is the central equation of the chapter. So why don't we finish up with using this equation with a theoretical question like so. The above reaction spontaneously proceeds to the right. Predict the sign of the enthalpy change and explain your prediction. So we are told that it spontaneously proceeds to the right, which means delta G is negative. Remember, if it's spontaneous, delta G is negative. Using our reaction, delta G is delta H minus T delta S, we can use it to analyze the possibilities. We are told that delta G is negative. Now, looking at the reaction itself, what we see is that we have ourselves a solid formed from two gases. And anytime you have a solid form, order increases, so disorder decreases. So we know for sure that delta S is negative. Disorder decreases. Knowing that delta S is negative, and knowing that overall delta G is negative, the only way for this to happen is for delta H to be negative. The reason being is because this term becomes positive since we're subtracting a negative. So the only way for delta G overall to be negative is for delta H to be negative. That way, if you add a number, it remains negative. And that would be essentially the explanation. So delta H is negative. You can also say this in terms of just theoretical ideas. We know that entropy is decreasing, so entropy is working against nature. And if nature is to run the reaction, then enthalpy must be working for nature. Delta G is negative because entropy is working against nature. And delta H must be working for nature. So that would be a way of explaining. You can also just explain it using the equation, but I think it's more fun to explain it in terms of what's going for and against nature. So that concludes lesson 3 of chapter 19.